OK, so let's talk about back to formalism. There's many more phenomenological examples you could do, but that's not our focus. Back to formalism, and back to this general power counting discussion. So let's consider an arbitrary diagram in this theory, this chiral perturbation theory. And let's enumerate some pieces of that diagram. So we'll say that it has some number of vertices. We just count how many times I've inserted vertices from the Lagrangians, and I'll call that NV. Some number of internal lines. Call Ni. Some number of external lines. The external lines are all pions. That's what our theory is describing. Could be kaons and etas if we're doing SU3. And then some number of loops. So we have an integer associated with each of these things. And when I talk about vertices, I don't want to restrict myself just to the leading order vertices. I want to talk about also these LIs and higher order vertices as well. So let me have a notation for that, where I take this integer NV, which counts all vertices, and split it into pieces that count the vertices at each of those different orders in the expansion in P. So Nn is the number of vertices that are order P to the n, or m pi to the n, or combinations of P and m pi to the n. But n of them. All right? So hopefully that's clear. So if I have 2 insertions of the leading order Lagrangian and 1 insertion of the subleading, then n sub 0 would be 2, and n sub 1 would be 1. And the total would be 3. That's what this notation means. So we'll assume we're using a regulator like dimensional regularization, so we don't have to worry about the regulator messing up power counting. And basically, that means we could ignore the regulator as far as this discussion is concerned. And we just count. And effectively, we can just count mass dimension. So we'll count lambda chi factors. Let's think about it that way. And we'll think about counting lambda chi factors for matrix element, a matrix element that I'll call curly M, which has NE external pions. So NE lines are poking out of it. So then if we look at the vertices, we can count how many factors of lambda chi there is. And I'm counting all dimensionful and turning all dimensionful things into lambda chi. And so each different order, and n, gets a different number of lambda chi's, because we even saw that already in the examples we treated, where we got f squared from the leading order. But from the subleading, we got Li, and that was dimensionless. So for n equals 2, which is the leading order here, leading order was p squared. I said that not quite right a minute ago. So lowest order is p squared, n equals 2. That's L0. And that had an f squared, and that comes out if I just have 4 minus 2, that's 2. N equals 4. That was giving our LIs, which were dimensionless. Okay, so you can see the formula working. And if we went to higher orders in the derivative and chiral expansion, then we'd start getting lambda chi's in the denominator. So this is just counting from the vertices, which you should think of as counting just from the prefactors in the Lagrangian. There's also f's that come with the pions. Because every factor of the pion field comes with a factor of f. You always have pi over f, and I'm turning f into 4 pi f for this discussion. I'm not worrying about the 4 pi's. You could do a more fancy version of this where you worry about the 4 pi's, but let's just focus on the dimensions. So if you have an internal line that's contraction of 2 pion fields, so that gets 2 f's, and an external line is just 1 pion field, so that just gets 1. Topologically, these different things that we enumerated are not unrelated. So the Euler identity tells us that the number of internal lines is the number of loops plus the number of vertices minus 1. And so we use that to get rid of ni. So then we can just put these things together. So if I get rid of ni here, then I replace it by nl. So that's that term. I replace it by the sum over the n's, which is the vertices, and then this gives me a plus 2. Okay. Now, that's not the dimension of the left-hand side. That's just the dimension of the ingredients. There's also things that are coming from factors of m pi or factors of p. And let me just call that something, e to the d, where d is just some number, integer, and then some function of logarithms of p over mu or m pi over mu. So e here is my, e could be m pi or p. And for the purpose of power counting, I'm not distinguishing, so let's just call it e, just to have a notation that could be either m pi or p. And then there's one more thing we can do, which is we can look at the left-hand side, and we can say, just by dimensional analysis, what should the matrix element, what should be its dimension? And depending on how many bosons you have sticking out, your matrix element should have a certain dimension, which you can figure out. And that dimension is just 4 minus ne. 2-point function would scale like p squared, et cetera. So now I have different things that are giving mass dimensions, the lambda chi's and the e's. But because I know what the answer has to be, 4 minus ne, I can solve for d. And that's what I got. Okay, so the answer for d, in order to get the dimensions right, we have to compensate for the number of lambda chi's by the factors of m pi and p. And when we do that, then we need this many of them in order to get the dimensions right. So one thing you see from this formula is that d is greater than or equal to 2. That's because these things are positive. The Lagrangian starts with n equals 2 and then goes higher. And when I add either of these terms, I cause suppression, or I stay the same. So this could be 0, this could be 0, or it could be bigger, but it can't be smaller. So you always get more e's, which are m pi's or p's, by adding vertices or adding loops. So when you looked at the loop graphs that were built out of the leading order Lagrangian, those terms had this be 0 because n was 2. But then you got suppression because we built loop graphs. So you got suppression from this term. And when we looked at the higher dimension operators, there was no loop, so we didn't have this term. But then we had a contribution from this guy, and that those were trading off. So having this is effectively part of what we need in order to make sure the theory is well defined, because it tells us how to organize the theory and what parts of the theory we need to worry about if we want a certain accuracy and what parts we can ignore. We need to know that we don't need to think about two-loop diagrams. And this tells us that we don't. Yeah.
I didn't understand where the D came from.
Yeah, let me say it again. So we figured out the lambda chi's by this stuff up here. Then I said, let there be an arbitrary e to the d, some parameter, which we haven't figured out anything yet. But I know just by dimension, I know by just what possibly this could depend on that it could also depend on mpi's or p's. So let me put some polynomial power in, and then some function that could be non-polynomial.
Right. Where would that? Can you give an example of like a calculation where I would see exactly what that is?
Yeah. So if you did this loop calculation we did a minute ago, we got a p to the fourth, and then d would be 4.
And those p's came from where?
Oh, they came from like the momentum going into. So if you looked at this diagram, yeah, there's p coming in here, and then it goes into the loop. Right, and this is derivatively coupled, so you get p's in the numerator.
Well, that wasn't taken care of with n.
Right, because nv is just counting lambda chi's, which are constants, not the p's. It's just counting the constants, the f's.
Okay.
Yeah.
Okay.
Yeah, and then you equate it to this, and then you get the d. Yeah, so you could have tried to set things up by thinking about counting p's instead of counting lambdas, but it's a yeah, anyway. All right, so what people often refer to this is they say it's p counting. Because you're counting momenta, and that includes p or mpi, but sometimes people call it p counting. And just to do some examples, when we had the lowest order Lagrangian, this guy comes out as 2 powers of p because there's 2 derivatives. And that, in our formula, is just the fact that d is 2 for that. When we thought about this loop, with leading order Lagrangians, which are scaling like p squared, we ended up having d equals 4. And the way that comes out of the formula is because of this loop term, which is 1. And then there's 2 plus 2 is 4. And this guy is 4 because of the explicit suppression. Okay, so the theory is organized as an expansion in this p.